First of all, Happy New Year, everyone. Hope it will be a good one for you. Thank you so much for inviting me. Thank you so much, Pavel, for the introduction. It's really a pleasure to be here. It's very cold outside, but it's really a pleasure to be here. So I think, yes, that's right. Compared to Sydney, it's very cold. So as Kevin already said, I guess this morning is a little bit on growth of various objects. And this is kind of a tandem talk with Victor. So I'm trying to motivate a little bit the type of questions in the beginning, and I will show you some examples of questions I would like to study. And I'm not 100% sure but what would have happened, but Victor then kind of takes over and continues the story. So let me just explain the graphs we'll see here. So this is one of my favorites. I stole that from a real paper, actually. And they were studying the growth rate of the number of publications per year. So there is this black line in the middle, which is kind of the expected value. And then they took various sources like Web of Science or something and just tried to, wrote down the number of publications. And on the y-axis, I put a log. So this is a log plot. So log plot really just means on the y-axis you put a log, and you can see that. It goes 2468, whatever, up to 20, and this is just the log of that number. And yeah, a line in a log plot means actually the number of publication grows exponentially, right? In a log plot, a line means exponential growth, and essentially that's what I'm going to talk about today in the setting of tensor categories, or symmetric tensor categories.
So this is a graph on the work of Tubbenhauer, editing of
The graph, I think, is not quite YouTube. But let me double check. I haven't double checked. Thank you so much for the question. And of course, feel free to interrupt me and ask questions. Okay, I want to motivate the problems we are going to study. And I start with something hopefully everyone likes and agrees on, the prime number theorem. Okay, so the number of primes, this pi function, so you just count the number of primes, is something. So I want to do something similar, right? It's a function that you can asymptotically describe very nicely, but really writing down an explicit value is kind of very difficult. I'll show you an historic example in a second. But essentially, I plot the number. So the number n is the dotted line. The pi function is the blue one, and the approximation, which we'll see in a second, is the gray one. And you can see the approximation is pretty good. And yeah, so kind of the question I would like to study of kind of the same type of flavor, there is something I would like to know. I would like to compute it, but I don't want to do the count. I don't want to count. I can't count. So I want to have some asymptotic answer to the question. And there are three different types of answers I would like to give. So the answer type 1 is that it roughly grows like n in this case. Right? So we will see roughly exponential growth or on the other ones, which essentially means that there is some correction term in front, and I will show you in a second what it is, times n. Okay, and people did that very early on. So Legendre, by the way, let me just say that. So the prime number theorem will say that the growth rate is around this, so the correction factor is log n. Yeah. And that was kind of well known. It took a while to be proven, but it's kind of well known. And Legendre tries to do that by just listing prime numbers up to a limit. So on the left-hand side is the n on my slide, and then the number by the formula is the next one, and the number from the table, so the prime number tables, is in the right column. And it turns out that there's a mistake in the table, which is corrected later on. So the first value is wrong, and the last value is true. But it doesn't really matter, I guess. So they were counting those numbers, and counting is difficult, right? There's a typo in one of Legendre's books. And they were trying to kind of find out what's going on. And Legendre was guessing actually this value here, which essentially said Legendre got answer 1 correct, but answer 2 wrong. So Legendre was thinking that the prime number theorem should be something like there's a correction term of minus 1.808. Turns out to be not true. And yeah, and it was a difficult task, and people were trying this a lot. So the answer 1 was kind of known for a long time. Just if you look at number tables, you will figure that out. And answer 2 took a while. So Gauss and Legendre were not able to do it. But eventually you get answer 2. There's an asymptotic formula, which is known as the prime number theorem. So the number of primes grows as n over log n. And by asymptotic means that the ratio is good. So I have 2 functions, and the ratio in the limit is good. And strictly speaking, I shouldn't say n log n, but because people really care about this logarithmic integral, which I'm just putting up here. But I like the formula n log n a little bit more because it's really like very explicit. So question 2, more difficult, right? We're doing some level design here. We're going up in difficulty. Question 2 is, can we write down an asymptotic formula? And this is not trivial. I'm proving the prime number theorem. It's not trivial. So the other one, just getting an overall grip on the overall growth, it's not so difficult if you want to give it a shot. But this one is well, it has a well-known proof, had many well-known proofs by now, but it's certainly not easy. Okay, so this is question 2 I would like to ask, if you want. Can I describe my numbers asymptotically? Okay, and if the ratio is good, right, the ratio is good, so here the ratio is good, that usually doesn't mean the difference is good. It usually actually means the difference is pretty shit. And the last question is about the difference between the expected value and the real value. And historically, this is the Riemann hypothesis in my example here, which essentially the Riemann hypothesis is a kind of really strange statement. If you see it for the first time, it doesn't make any sense. You're counting, you're looking for zeros of a certain function you don't care about. They're supposed to lie on a certain line. You don't care about that line. But essentially what it says is, so Riemann wrote down, in the paper you'll find that, so f in Riemann's notation is essentially what is pi in my notation, and Li is a logarithmic integral. So pi is Li up to some error term, and the error term, as Riemann writes here in German, I will translate in a second, down here, runs over all non-trivial roots of the zeta function. Yeah. So that's why people care about those roots of the zeta function, because it gives you this error term in the approximation in the expected value, the logarithmic integral, and the real value, the pi function. And as you all know, this one is really like super difficult to prove. Yeah. So we're going up in level design here. It goes more and more difficult as we go along, right? Okay. So what do you get from the Riemann hypothesis? Assuming that it's true, you can get that the difference is bounded by this value, where the 1 over 2 is exactly the maximum number of a real value of a root of the zeta function. Okay, and that's what I call the variance, because it's like the variance of the real value from the expected value. And I plotted that for you, and it's actually not so bad. Okay, let me write that down. Okay, so the value itself grows roughly like this. And of course, you can ignore the log. And the variance grows roughly like square root of n. Of course, the Riemann hypothesis is true, times the log n. And you can ignore this. So this still grows as square root of n, and this just grows as n. It's something very similar in a second. So this is really actually pretty shit if you want. So the difference gets arbitrarily large. And again, level design question number 3, what is the variance from the expected value, is like ultra difficult, right? The Riemann hypothesis will probably not be proven in the next, 1,000 years or so. But this time the evidence is like really, really huge, so it's true anyway. Very good. We'll see something similar. And I'm going to answer question 1. I explain in a second what my setting is. And then I'm partially answering question 2 and 3, which are like really, really difficult in general. Turns out question 1 has a really beautiful answer. All right, that's my setting. And I guess this is not a prime number conference, so maybe, again, I have a log plot here. A line in a log plot is an exponential function. And let's just be vague for now. Let's just say we have gamma is something that has a tensor product. So I can write down a tensor product of my whatever I do, and it acts on V. Gamma acts on V. And let's say then I can get an action on v to the n, and I want to decompose this space, right? Very similar to Kevin's talk, but I'm looking for the indecomposable summand. So I want to decompose the space, and of course, as you might note, the dimension of this space is of course just the dimension, our little exponential grows, dimension v to the n. So I want to decompose the space. And in this generality, well, let's say gamma is a group, arbitrary group, right? K is any round field, V is any finite dimensional representation. So in this generality, I can't say anything about it. Right? If you just take the symmetric group if you want, and V some finite dimensional representation, then really giving a combinatorial formula for the decomposition is something like the Kronecker problem, which is like notoriously difficult and still open since the 30s when it was posed. So in this generality, there's no hope I can say anything. It should remind you of our little example with pi, because this is a number. If I want to count this number of indecomposable summands, which I'm going to tell you about in a second, then there's just no way I write that number down. But maybe there's some nice asymptotic answer for that setting. Okay, what gamma could be is any group, any monoid, any semi-group even. Right? So kind of fun fact here, semi-groups always form a monoidal category, so representations of semi-groups. It's not rigid because you don't have an inverse for the Hopf algebra structure, but we can always use those, and anything goes essentially. So there's superversions. I'm not going to talk about the superversion a lot, but everything I'm going to say applies for supergroups as well, and in even a bit more generality. And actually, essentially everything goes. So the only thing you ever need is something like I will be very precise later, something like an additive Krull-Schmidt monoidal category. And then you can play a game like this. Essentially, I only need that this problem makes sense, that I can decompose my space into summands. And then I can actually get an answer. Okay. So this is not going to happen, so let's answer a different question. So what I want to do is I motivate now SL2, and I prove everything for SL2 for you. Okay, so I take SL2. Hope everyone likes SL2, my favorite. SL2, very harmless over the complex numbers. And I take its two-dimensional defining representation. So I act on a two-dimensional space. I take that space. I take tensor products. And I want to count the number of summands I see. In this case, everything is semi-simple. So simples is the same as indecomposables. So count number of summands. All right, and this is, let me tell you a story. This is how I ended up in this setting. So Victor was giving a talk in Oberwolfach and had a conjecture on the board, which I'm going to show you in a second is a theorem. Oops. Which had a conjecture on the board, and which I'm going to show you in a second is a theorem. And I was like, Victor, that's stupid, that's wrong, okay? Of course, Victor was correct. And I was like, I can prove you're wrong. I have a computer program who can do SL2 in the notoriously difficult case where I go to characteristic 2. So characteristic 2, SL2 in characteristic 2 is like really strange. I have a computer program, can do this calculation for you. I prove you're wrong. Turns out Victor is right. But the problem is, so some people just grow exponentially, you know? You just need to, and then Victor proved it. Victor and Kevin proved it. So you just need to spur them on if you want. So the plot I made at that point was, so I listed the 1000th tensor power. So this guy to the 1000 in characteristic 2. This is just characteristic 0, and made a plot like this. And what you will see is that the number of summands grows very, very fast. But what do you do if you expect exponential growth? You just take, so this is Bn. You just take the nth root if you expect exponential growth. And what you see here, the blue line is the nth root of Bn. And the straight line is just the number 2, So this thing converges to 2, which you can easily see from the plot. So log-log plot means I do the same on the x-axis. And yeah, it seems to converge to 2. So the thousandth root of the thousandth symbol here is 1.99265. Convergence is really shittily slow. Here comes my story continued. So here it's even slower. It's just really horrible. So I was doing this calculation. My program wasn't fast enough to do the thousandth power. So I just spent the whole night in Oberwolfach making the program faster so it can go up to whatever, the thousandth power. Nowadays, it's much faster. Nowadays, it can do the 1 millionth power or something like this because it uses a different strategy. But at this point, I was spending the whole night trying to disprove Victor. And yeah, it turns out Victor is right, of course, that the limit is 2. So if you do this in characteristic 2, same type of question, then it's even at the 10,000th power, it's still around 1.9. It's not quite clear what the secret is trying to do. So I was really disappointed. Had no result at all. And eventually, Victor and Kevin proved that this number converges to 2 in arbitrary characteristic. But let me prove it for you for SL2 in characteristic 2. Okay, so how would you do that? Okay. So the representations, the simple representations of SL2.
Daniel, actually, that work is better because it doesn't.
This one works better.
Yeah.
I was told the other one is better because of the camera, but hopefully that will work out. Anyway, so if I write down representations of SL2, to me they look like the binomial theorem. So this is a trivial representation. I just write down the weight space. This is a 2-dimensional one. This is the next one, and so on. Just write down the weight spaces. And if you write that as a character, you can say this is 1, this is q plus q inverse, 1 minus 1, this is q squared plus 1 plus q to the minus 2, and so on. And all I need to do is I need to decompose this guy to the n, which is the n standard power of this one, into this basis. But the only thing I need to observe is that it goes through the middle. So everything up to a parity issue, everything cuts the middle exactly once up to a parity issue. So on my Bn number, it's just, because this is a binomial theorem, just the middle coefficient. So it's just really n over 2, and because that's a parity issue, it's like this. N choose n over 2, and Stirling's formula will give you n over 2 is something like 2 to the n, square root of n, 1 over square root of n, and some scalar, whatever. And if you take the nth root of this beast, yeah, the 2 survives. Nothing here has a chance against the nth root. So the nth root is really just 2, which would prove exactly our theorem in this case. And observe here, what I have here is essentially the same as in the prime number theorem. I have some leading growth, and I have some sub-exponential factor in this case. And the sub-exponential factor dies if you take the nth root. Right? The nth root is a really brutal operation. It just kills the sub-exponential factor. All right. So in this case, what I wrote down is the following. The limit.
Actually, there was a line there, and there was a request not to write below it.
Oh.
This thing here, which
Excellent. There was a line here. It should be around here. What we just saw is the limit n to infinity of the nth root is 2, which is the dimension of my starting space. Excellent. And this was Victor's original claim, that this is actually true in general. Okay, so I continue. Well, the next one, you try maybe the 3-dimensional representation of SL2. You do the same, and the number will converge to 3. Well, and the thousandth one is now, convergence is really shit. It's now 2.98, but sounds very believable that this is true. And yeah, so everything that works for SL2 should be true in general, right? So that's just my general strategy. So let's say you take, well, an affine semigroup superscheme, whatever. Take a group and ask the same question. A general group, not just a finite group, what is the number of indecomposable summands? You can easily see that this number that I call beta, which is this limit, exists, follows from by submultiplicativity in this case. And you ask the question, what is this limit beta? It's somewhere between 1. 1 just means everything is one block. And the dimension, it can't be finer than the dimension, because that's the dimension of my space. So it can't be finer than that. And if it's dimension, it's kind of fun. So it's somewhere in between. If it's a dimension, and this really just means everything is kind of really, really tiny compared to exponential growth. And exponential growth is really scary. Remember that this guy here grows exponentially. And if this number is 1, that kind of, it really says, it wants to say that it looks like this. There's some sub-exponential correction factor, but essentially the growth is exponentially. And it turns out that this is true. So yeah, so for anything is on the previous slide, any semi-group, this is actually true in any characteristic for any representation of your group, that this limit is always the dimension of the space. So in all of these settings, no matter what you do, indecomposable summands are really tiny compared to exponential growth. Okay, let me do that. Let me show that how that works for SLN, how you can do it for SLN in characteristic 0 again. And maybe it's clear what I mean by they're really tiny. First, SL2. Everyone likes SL2. Okay, if I do SL2, well, then the dimension of my indecomposables is actually really simple because they're all just those guys. And the dimension of that space is, that's a good question now, k plus 2, something like that. Some polynomial in the weight, if you want. And if you take this tensor power, this was c squared, the maximal one that appear will be n plus 2 or something, or n plus 1 probably, off by 1 error. So the maximal summand that appears is of this dimension. So the worst case would be that the dimension is everything is maximal. Everything, I'm thinking about decomposing, filling the sun with the planets, and now I assume that everything is Jupiter. Right? There's still a lot of space for Jupiter. So if everything is of this size, then my Bn should be definitely bounded by 2 to the n divided by whatever kind of thing I see. And it's also clearly bounded by 2 to the n above. Now take the nth root, it's sandwiched in between, and you get your number. Let me do the same for SLN. Again, you could do that for any representation, but anyway. Take the defining representation, I take its tensor power. N is probably bad, let's take m. Take its tensor power. What is the maximal thing that turns up? Well, you can kind of estimate what it is, but Weil's character formula will tell you that the dimension will grow polynomial in the weights. Polynomial grows in rates in the weights, which immediately implies that you can again divide this one by some polynomial, take the nth root, it squeezes, and it's gone, right? So again, Bn is bounded by dimension of v to the n divided by plus some polynomial. And you have your result. And what do you do in general? Well, essentially that's what you do in general. Now let me try to indicate how the proof goes. Well, instead of doing it like me, like writing a computer program and realizing that you can't say anything because the growth is so bad, what you should do is you should just ask Victor and Kevin, and they will tell you the following. So let's say gamma is a finite group. Finite group.
Wait, Daniel, can you?
Yeah.
This theorem at the bottom. Can you say what in which generality that goes?
Sorry, I can't hear you.
This theorem at the bottom. Can you say which general setting it goes?
Sorry.
The
Yeah, that's better.
bottom. Can you say in which setup it goes?
Yeah, for any if gamma is any affine semigroup superscheme. Essentially, what you need is a category and a symmetric fiber functor to vector spaces, so they could make sense of definition of dimension. Any semigroup works. Any representation, any finite dimensional one. Okay. In particular, any finite group. And the only thing you need to know is that some power, there exists n, such that v to the n contains a projective summand. Okay, something contains a projective summand. And for a finite group, this just means as soon as you have a projective, it will form an ideal. So everything you throw at it will give you projectives. But I think about it as like this picture. I take my tensor power, and I'm looking for, so I take those tensor powers as n increases, and I'm looking for projective summands. Eventually, I will find one somewhere here, and it will form an ideal. It will span a cone. And everything here will then be projective, because everything you throw at the projective is projective. And if I think about this picture of a cone in a cone, well, if I zoom out enough, and my little point is down here, then essentially everything eventually will be projective. There you go. Okay, so everything is projective. In this asymptotic setting, you can somehow ignore what's happened here. Yeah, just ignore that. Everything essentially will be projective. But for a finite group, there are only finitely many projectives, so I can play my little Jupyter game, divide by the biggest projective dimension-wise, and I would get the statement. Turns out that the proof in general is not much different from this one. Essentially, have some proof like this. I hope that makes sense, right? So if I have some projective somewhere, it just spans a cone because everything you throw at it will be projective, and eventually everything will be projective. It's up to some fluctuations, and the fluctuations are exactly what gives you the sub-exponential factor in kind of this expected formula. Sorry?
So instead of using some projective object, you could work with some object generating a tensor ideal with finite dimension.
Yeah, exactly, yes. That's the main point. Okay. Right. So you have finitely many projectives. Excellent. And the proof in general is not much more difficult. Essentially, you need to work with the general linear group and replace projective by tilting if you want. Okay, but this is essentially the proof, and it's kind of a nice statement. So for essentially anything, you can kind of estimate the overall growth factor. Okay, so I have 20 more minutes. So the natural question that comes up that I would like to answer in the next 20 minutes is, can you say something about this one here, right? So if you know in quantum generality that this one will be the leading growth rate, can you say something about the sub-exponential factor? In particular, can you write down some formula of this type? Bn is asymptotic to whatever times some sub-exponential factor. So this guy will always be around times the exponential growth factor here. Excellent. So that's what I want. So it turns out that this is kind of really easy in certain settings. I want Bn to be whatever, and I will call the asymptotic formula An. So I wanted to know this asymptotic formula. On the next slide, I will probably just do that on an example, but essentially it turns out that this is an eigenvector and eigenvalue problem using the famous Brown Frobenius dimension in a certain generality I'm going to explain. Okay, let me just do it on an example. So for now, let's assume we have some finite problem where we only have finitely many indecomposables, and I want to know what this number here is in front. So what you do is the following. So I take here the symmetric group S3. I write down, I take the only interesting representation of S3, the two-dimensional one, well, that's probably not the only one, but I take the two-dimensional representation of S3 in characteristic 0, and I write down the fusion graph, and it looks like this. So this is the two-dimensional one, and let's say this is the trivial one, and this is the sine one. So if you tensor the two-dimensional one with itself, it will spit out a copy of itself and 1 and 1. So if we write down the matrix, it looks like this. And the matrix is really just tensoring. So this is the matrix of tensoring with this dimension, this representation. Right? I just evaluate it on the trivial one. Tensoring the trivial one with this one gives itself. Tensoring the sine gives itself. Because it's this representation. And tensoring with itself gives everything. Okay. Write down that matrix. The leading eigenvalue of that matrix is called the PF dimension. M. M of my problem is the leading eigenvalue. And that's exactly the dimension. So this is our leading growth rate. If you think about this, well, this problem encodes tensoring with this guy, and taking its nth power corresponds to taking the nth power of the matrix. What determines the growth of the nth power of the matrix is the leading eigenvalue. And in this case, it's really just the dimension of my representation. In order to get the asymptotic growth rate, which is in this case just 2/3, what you do is take the corresponding leading eigenvectors. Well, there will be 2 of them, V and W. In general, there will be 2. There will be a left one and the right one. In this case, the matrix is symmetric, so they will be the same. And you write down a formula for them. You just put them together. You get another matrix, whatever. And the row sum of the first row is the number you're looking for. You take the sum of the first row, that's your number. Okay, and that's exactly this 2/3 if you do it in this example. 1/6 plus 1/3 plus 1/6 is the 2/3, and that's the asymptotic formula you get. And I just plotted the ratio. It converges like really fast.
Can I ask a simpler example? Z3 cross Z3 and characteristic 3.
Z3 cross Z3, which representation?
Well, it's a wild.
Right.
But there are lots of. I don't see where these indecomposables are.
No, so the point is that some tensor power will always contain a projective.
Yes.
And then when you keep tensoring, the most of the stuff will
I know that's what you. Okay.
So the rest will grow like this. So you have dimension of b to the n minus the dimension of projected to the power k over n. So it's going to grow slower. It's not going to contribute.
And is it some analysis like this looking at leading coefficient of something or other?
Well, for finite groups, it is more.
For finite groups, it is exactly this, yes.
But for algebraic groups, it's not trivial and requires analysis of dimensions of tilting modules, so they can only get big on the boundary.
That's right. For finite groups, it's really just this. For any finite problem, it's just this.
For algebraic groups, it requires.
So this matrix you do, this is just a matrix how you multiply by V, right? It's,
Yes.
Uh-huh.
But really, you have to do it for G.
I can believe that.
Right, so you write down the matrix you get by tensoring. Its eigenvectors and eigenvalues will completely determine the growth problem. In a very easy sense. So the leading eigenvector is the overall factor, and you get this one from the leading eigenvectors. And the leading eigenvalue is this one. Okay. Here's another example. So it can happen that the leading eigenvector is not unique. You can have them around the. Perron-Frobenius will tell you the following. Perron-Frobenius will tell you that there's a leading eigenvector leading eigenvalue is somewhere, and all the other eigenvalues are somewhat smaller. But you can have it repeated like around the circle. That can happen. It's called the period. So here's our leading one. This is, in my problem, this is the dimension. And then you can have it repeated around the circle. And if you just think about it, they kind of should, maybe do the easy example of the circle itself. So if you have here the dimension and here you have minus the dimension, what they should do is they should somewhat, depending on parity, go hand in hand, just pushing the growth or kind of compete with one another, depending on parity. So your sub-exponential function should be something that oscillates, in this case, between even and odd things. And what you do is, well, let me go back to the formula to get the formula if that happens. What you do is you have now many of them, right, up to h, which is the period. This is 0, 1, up to h minus 1. H is called the period of the problem. They lie around the circle. Everyone has an associated eigenvectors. You do the same formula, but now you go through the roots of unities in the formula and just add them, and the leading growth is still what it is. Like in this example, my two eigenvectors are 2, and eigenvalues are 2 and minus 2. So I have 2 and minus 2. You have two associated eigenvectors. So here I have the leading eigenvector are 2, minus 2. I have associated eigenvectors. And if you do the formula, you get exactly the sign. So well, what is the second root of unity? It's a sign. So you get exactly this 3/4 coming from those eigenvectors, and whatever it is, a 1/4 coming from those eigenvectors. And this is your sub-exponential factor. Right? So it oscillates between, they work together when n is even, and they kind of compete a little bit if n is odd. And you can literally do that. It's kind of a fun problem. So pick up your favorite finite dimensional category, and you can just do it. For symmetric group, you could get some nice formulas that you can write down. So I did quite a few different examples. You can do it for the dihedral groups, for whatever. Pick your favorite group, pick your favorite representation, and it's a matrix and eigenvalue problem. Okay. So for the symmetric group, we get this nice result, which I think is due to Pavel, Kevin, and Victor, that whatever your representation you take, well, you have the exponential factor here, and then the correction factor does not depend on the representation. It's kind of a universal correction factor. So the only thing that depends on the representation itself is the scalar in front. And that's kind of true in some kind of quite large generality. So it's kind of fun that in this asymptotic formula, usually this factor doesn't really depend on the representation itself. And that's, for example, true for any finite group. Okay. Excellent. 10 more minutes. I did a few more examples. You can do Verlinde categories. As in the previous talk, you get some funny formulas. So the eigenvalues of the Verlinde categories are always those funny cosine numbers, the largest ones, and you get those formulas. Literally everything, right? So I'm not restricting anymore. Just any finite tensor category makes sense. Here's another example. You can do Verlinde categories for SL3, for SL whatever. You can just write down the formulas, and it's not all that difficult. It's kind of a really nice answer. So this guy here is always kind of the exponential factor is always the dimension, Perron-Frobenius dimension, and this one is always, at least in this finite case, always given by some eigenvector and eigenvalue problem. And you might wonder in what generality is that actually true? Well, let me just tell you one more thing. So here's SL2, again, in characteristic P, and many more formulas here. Okay, so it really is just this pattern where the overall growth is exponentially, and then you have a correction term coming from the eigenvectors. Excellent. And now there's question number 3. What is about the variance? Well, if you think about the problem that this guy grows roughly like the leading eigenvalue vector, which kind of messes up the growths, it's the second largest eigenvector value. So the second largest eigenvalue in this case gives you the variance of the problem. For example, for SL2 over F5, taking the defining representation again, the largest one is 2. The second largest turns out to be the golden ratio, and there's a really, well, in this case, it's almost spot on. If you take the golden ratio to the n, so the variance in this case is quite large. So for SL2, for example, SL2, I take F5, I take F5 squared, I act on F5 squared. The leading eigenvector value is, well, 2. So lambda leading is 2, and lambda second turns out to be the golden ratio, so 1.618. So this guy grows as 2 to the n, and the error, so the difference between the asymptotic formula and the real formula still grows exponentially with this guy to the n, which is much, much slower, because one of them is 2 to the n, the other one is 1.6 to the n. So this one is still much, much slower, but it's still exponential in growth. Okay. Let me just summarize what we have seen. So answer to question 1 is, in quite some generality, it's always exponential growth. Answer to question 2, at least if your category is finite, you write down an eigenvector and eigenvalue problem, and just do this one, just do an eigenvector and eigenvalue problem. Okay, what I observe here, let me just write that down. It's the following. And answer to question 3 in this case comes for free. Again, it's the second largest eigenvalue that determines the variance in this case. So question 1. It's always v to the n is the overall growth rate. Question 2, if my problem is finite, so let's say if problem is finite, so I have only finitely many decomposables, is finite, then an, so the asymptotic formula, is an eigenvector eigenvalue problem. And question 3, kind of same assumptions, then it's again an eigenvalue problem.
What did question 3 again?
Sorry?
Can you repeat the question 3 that you answer now? Just repeat the question 3.
That doesn't work. You need to take it off.
Can you just repeat question 3?
Question 3 is question 2 is about the ratio. Question 3 is about the difference. Okay, and then I was wondering, in kind of what, essentially, coming back to your question, in what generality does this actually work?
Well, it's an eigenvalue problem for what? Can you repeat question 3 again?
Sorry?
The answer in question 3 is an eigenvalue problem for which element?
For the matrix of given by tensoring with your defining representation. This is a representation you want to study. Let me do that. So this is, you have a representation, V, okay? You want to know what this guy does. You write down a matrix where here this varies over all simples.
No, I understand the question, but
The question, how is the question C, you know, other things like this.
Ah, okay, okay, good. Yes.
Thank you for answering the question I didn't understand, Victor. Excellent. My question, though, is in what generalities is true? And I probably shouldn't write so low. And I'm running bad on time, but let me just tell you the answer, or at least as far as I know. Essentially, it's true in the following case. It's true in any finite case, but it's true if the random walk you will do on your, let me just explain that in words maybe. All right, I have a matrix. This matrix corresponding to tensor units by representation. Like this guy. Whenever I have a matrix, I have a graph associated to that matrix. I have a graph where just every row and column is a vertex, and you connect them. So I connect 1 to 2. I connect this guy to everything. So I probably should draw it like this. And I connect this one to this one.
So do you want
The last is also connected to itself.
You threw an extra one.
Oh, I'm sorry. It was this matrix before. Now it's no longer connected to itself. Problem solved. Okay, so you write down that matrix, and it can be an infinite matrix. It's always a countable problem. You write down the matrix. You get some countable graph, whatever it is. Whoop, 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 whatever. Something. And you do a random walk on that graph. Okay? So you do a random walk on that graph. And, okay. You do a random walk on that graph. And I call the random walk recurrent if the probability of hitting every vertex infinitely often is 1. And I call it transient if the probability of moving away is 1. Okay? So if you think of everyone's favorite random walk on the integers, then it's, right, you can move like here, whatever, do a random walk. And I'm looking for the probability that I return to the origin. If the probability is 1, then I call it recurrent. If it's not 1, if it's 0, I call it transient. Transient means you go away from the origin. And it turns out that the problem before has an answer whenever your problem is recurrent. So those guys work for all recurrent problems. Okay. Sorry?
Is that, I mean, can you say what that means in terms of your representation situation, or is,
Yes.
or is that just?
I will.
Okay.
So for a self-2, for example,
Sorry?
for a self-2, what is happening?
I will answer your question. Okay. Let me just tell you what I know about this. So skipping a few slides. Okay, so a theorem that you can essentially pull up from a famous paper by Polya, the original paper where Polya discusses random walks on lattices, and turns out that the Z lattice walk is recurrent, the Z square lattice walk is recurrent, but the cube one is not recurrent. It's this famous theorem that the drunken bird will get lost. Yeah, a drunkard will find their way home, the drunken bird will get lost. And you could pull that for representations, and you get this statement that the problem is recurrent for a representation, and in characteristic 0, in characteristic p, I have really no idea what's going on, if and only if my group is virtually a torus of very low dimension. Virtually means you can always extend by a finite group. Finite groups do nothing. Excellent. So SL2 not on this list. SL3 not on this list. All finite groups, yes. So for everything in this setting, you can imply, and this is if and only if, you can apply the eigenvalue strategy. I'm essentially out of time. But let me show you, well, in characteristic P is like really difficult. I have no idea what's going on. Okay. Let me just give you,
So for this, for which groups?
sorry,
This is
for all finite groups and the additive groups z to the d for 0, 1, and 2 extended by a finite group.
But initially, gamma is what?
One of those. I should have put gamma on the slide. Gamma is one of those. It's virtually z to
When we say equivalent, this is for which class of groups? This theorem.
gamma is of this type.
There, those
No, but on the left.
Also gamma.
Right, but what kind of for which gammas?
those.
Those such that the category of representations looks like.
I don't understand the question.
Gamma on the left hand side is a generality.
Yeah, that's what it was.
On the left hand side, so you have a statement on some gamma, but gamma.
Wait, we have finite gamma as well, right?
Yeah. Virtually just means finite is included.
What is the setup of the statement?
Sorry?
This is the statement. I mean, the statement is you get one of these groups, but
Yeah, but gamma for him is just something super general.
But what is the statement?
Okay, the statement is badly formulated.
Just any group gamma was fine.
Yeah, any group gamma, and then it's recurrent if and only if gamma is of this type.
And when what? If the graph is
Then you can answer the question.
I think it's Q3.
The same strategy applies.
So gamma is finitely generated.
Yeah, probably gamma is something like finitely generated.
So in this case, you should consider the Zariski closure of gamma,
Yes, exactly.
and this should be its Lie algebra should be it should be an extension of a torus.
That's right.
A finite group.
That's right. I will just prove the theorem. That's very good.
The torus of dimension at most two.
At most 2. Okay. Let me just give you one more case, and then I'm probably over time anyway. Actually, any finite tensor category is recurrent. And that's not trivial, because finite tensor category doesn't mean it has finitely many indecomposables, right? So any finite tensor category is recurrent. And then there's one more case. So for any SL2 in characteristic SL2, SL3, any reductive group in characteristic 0, you can write down a closed formula, which is kind of really mysterious to me, because this is not a recurrent case. So the formula comes from somewhere else. Comes from the theory of generating functions. BNA did this like 20, 30 years ago. You can write down everything. You can solve the whole problem. So BNA gives you the overall growth rate, it's kind of crazy formula, a scalar depending on the root system, and then even the variance. And this is really mysterious. So it still works, but if you go to characteristic P, even SL2, I have no idea what's going on. So the function is like, the function in front, the Cn, I just plotted it, it's like crazily oscillating back and forth. Okay, that's all I have to say. Thank you so much.